Hey everybody. So this video we're going to talk about something called vector functions and space curves. So we've already seen vector functions. I've even called them that a little bit, but I haven't been making a big deal about them. The equations we came up with for lines in previous videos, those really were vector functions. So let's take a second here and think about what functions are in general, right? When we have a function, the way we think about it is we have a domain, and you pick anything in that domain. A domain is just a set of objects, and we take that domain, and for each object in it, we associate an object in the range, right? So if I I can name these things anything I want, some object D, that's a piece of the domain. I make a rule that says for each one, there's some object in the range, right? So the most typical functions and the vast majority of functions we've looked at in our mathematical careers up to now are functions where the domain and range are both numbers, right? You put in a number, I put in the number 2, and my rule says the number 2 is associated to the number 4, and the number 3 is associated to the number 9, right? It's the function that that squares them. So in that case, the domain and the range are both sets of real numbers, right? But they don't have to be. They don't have to be numbers. They don't even have to both be the same thing. For instance, at the end of each quarter, I create a function where for each name in my class roster, I assign a grade, right? That's a function. Each input is a student, the output is the grade. Or I could input a student name and output your student ID number. Or you could input a year and output who was president on January 1st of that year. That would be a function, right? The domain would be all the years that there are presidents on January 1st, and the range would be the list of people who've been president on January 1st of all those years, right? So all of these things can be functions. So the functions we're going to talk about now are vector valued functions or vector functions. Okay, so all this means is that the domain for the kinds of functions we're going to look at, they're going to take numbers, in real numbers, that's the input, that's the domain, and what we output are going to be vectors. Okay, so I'm going to write Vn. Typically, we're going to look at three-dimensional vectors. That's what we're typically going to be dealing with, right? And so we'll use a symbol, something like we most often will use T as our input, and we'll output some vector function. Okay, so and what these vector functions will look like. Right, one way we can think about them is there's a function for x, there's a function for the y component, and there's a function for the z component, okay? So we'll do some examples in a moment, but just look at what's happening here. T is a real number. I input a number t. Each component, we call these the component functions. Each of these is a function from the real numbers to the real numbers, right? I put in a number t, then I spit out a new number x of t. But because we're doing this 3 times and putting it in as a vector, this function in its entirety is spitting out a vector. You put in one number t, you get the 3 component functions to spit out numbers. And so what you get is a vector. Right, so remember the equations we came up with for equations of lines, right? We would input, well, let's just write one down. If I wrote the equation r of t equals t minus 1, 2t negative 2t plus 7, something like this, you might recognize this as an equation of a line, right? I could also write it as negative 1, 0, 7, plus t times, we have 1, 2, negative 2, right? For each value of t, I spit out a number in each of these components, and what I get is a vector pointing at a point on the line, right? So again, I want to keep that distinction between the points on the line, or the points in this function. We'll see these are going to be what we call our space curves, but these are actually vectors, right? So they're vector functions. We don't think of graphing them the same way as you graph functions where you draw the sort of the shape of them. We'll visualize them in just a moment. One thing that's nice about this, actually, let me write this in one more form. So we can also write this as the x function times I hat plus the y function times j hat plus the z function times k hat. Just another formation of this, right? So again, it's kind of like these, one way to think about it is these functions are scalar functions, inputs real numbers, output real numbers that scale our basis vectors to build the vector we want, okay? A couple of quick things before we dig into some real examples. Because these vectors are defined with functions that we're familiar with, that is real valued functions, functions from real numbers to the real numbers, we can use a lot of the same, we can use very simply modified versions of some of the stuff we used for these functions, for our real valued functions on these vector valued functions. For instance, we can define the limit as t goes to some number a as the limit, oops, sorry, oops, I forgot a whole bunch of things. The limit of our vector valued function is just the limit of each individual component. Right, limit t goes to a, z of t, provided these all exist. So if all three of these exist, right, if we are getting t closer and closer to some value a, and when we do that, the x function gets closer and closer to some number, and the y function gets closer and closer to some number, and the z function gets closer and closer to some number, then the vector is going to get closer and closer to the vector built of the components of these limits, right? So if, you know, in a simple example, if we look at the r of t we just had down here, if I said, what's the limit as t goes to 0 of r of t as defined down here? Well, it's just the limit as t goes to 0 of t minus 1, the limit as t goes to 0 of 2t, and the limit as t goes to 0 of negative 2t plus 7. And these are all simple limits to take. The first one, since they're all polynomials, they're lines, in fact, we can just use the substitution rule. We get negative 1, 0, 7, right? So the limit as t goes to 0 of this function is r of t. The limit as t goes to 0 of r of t is just saying that as t gets closer and closer to 0, the vector that's coming out of this function is getting closer and closer to this vector, okay? And we can define continuity in a very similar way that we have in the past. We would say R is continuous at x equals a. I'll just say at a if the limit as, not x equals a, as t goes to a. The limit as t goes to a of r of t is equal to r of a. Right? Which means each of these functions in here is equal to its limit, okay? So we're just kind of piggybacking on the old definition. I'm not gonna say much more about this right now. We're going to, in a later video, dig into some calculus on these vector functions, at which, like things like derivatives and integrals, at which point we'll have to revisit this stuff a lot. But it is pretty straightforward. If we ask you to take a limit, it's just saying do these 3 limit problems, okay? And as we get better at visualizing these vector functions, the meaning of that might become clearer. When I do a video on vector derivatives, we'll spend a bit of time visualizing what these limits look like. All right, so let's look at some of these vector functions. It's kind of hard to understand them if we don't really take a good look. So I'm going to open up a picture of them. Let's see. There you are. All right, so the first function I want to look at is going to be the function r of t is equal to t squared t cubed. Okay, so remember, it's a vector function. It's going to be spitting out vectors. So right now, let's see, this red arrow is the vector. Right now, this is the vector at the point where t equals -1.5. So I'm going to start changing the values of t. Right, I'm having the vectors begin at the origin, and notice there that as I change t, that vector is changing. Let's put in a value of 2 and see what we're looking at. So at 2, right, we expect r of t to spit out. Let's just write it out. R of 2 should be 2, 4, 8, right? Well, let's just look at the vector that we have. So, oops, sorry, let me erase that. There we go. So let's look at this vector that we'll have. So right now, the red axis is the x-axis. And if you look along that axis, right, it looks like this red vector is out about 2 units in the x direction, 4 units in the y direction. We're looking down the z-axis, so we can't really see the change, but so far the first 2 components work. And if I turn this so I can see the height of this vector, it does actually match up perfectly with the top of this axis. Let me zoom out, oops, wrong way. Right, and we can see that that vector's up 8 units, right? And so for each value of s, we have a similar thing, right? They're all changing as I move, and we're spitting out all of these vectors, okay? That's one. Let's also look at let's look at the vector function p of t is equal to cosine of t sine t t. Okay, let's take a look at this vector function. Turn the first one off. And again, it's a little tricky to get a sense of this thing, right, when we're just looking at the vectors. So there's a neat little visualization that we can do. We can connect each of these vector functions to a set of parametric equations. For instance, well, let me write this off to the side. In general, if I have a function, you know, r of t equals x of t, y of t, z of t, I can think of the corresponding parametric equations. All I'm doing is changing the hard bracket to a soft bracket and thinking of it as something that spits out a set of points, right? So just like with the lines that we dealt with in previous videos, we can think of, we could kind of, we get this vector function that is going to be points pointing. Well, when we're doing lines, we had vectors pointing at points on the line. So the vector is different than the line, it just points at it, but then we also think of the line as the set of all those points, right? And there's this connection between the two. Well, we're doing the same thing here. It's just that we don't have lines. We have different shapes for our curves, and these are what we call space curves, right? So this set of points, as t goes through its domain, spits out the space curve. And for domains here, we'll use the same convention that we usually use with real valued functions. That is, if I don't tell you a domain, if I say f of x equals 3x squared, we generally assume the domain is all values for which the function is defined. So if I said f of x equals 3x squared, it's defined for all x. That's our domain. If I said f of x equals 1 over x, all x except for 0, right? If I need a special domain besides what's mathematically necessary, then I put that in. So the same thing here. We'll assume the domain is all the values that make these functions definable, right? So in the two functions I've given here, they are defined both for all real numbers, right? Although with this graphing software, I have to give it a finite domain, so I can't graph it for all real numbers. So let's look at that first function. This r of t is equal to t, t squared, and t cubed. Let's look at that and see what the shape actually is. So I'm going to start by looking just at what happens between x and y. So in the orientation I have right now, the red axis is the x-axis, the green axis is the y-axis. We're looking straight down the z-axis. So this is that perspective where we're going to ignore the z information, right? If I draw a point here, right, you can tell that the x-coordinate is 4 and the y-coordinate is 4, but you can't tell how high it is in the z-coordinate, right? So we strip away visually all of the vertical information. So what should this graph look like? What should this space curve look like? Well, if I look at, we're looking at r of t, the relationship between x and y is always the same value as x except squared. And so we would expect to see the relationship y equals x squared. So let's look at, now the curve is graphed. Notice it stops. This is the limits of my the graphing computer software, because I have to give it some kind of domain. There's also another thing why we're not seeing very much of it that we'll get into in a second. But you can see that familiar shape of a parabola. However, let's now turn the axes and we see that there's a lot more going on, right? So there's this strange kind of curve going on here. Let's look at another relationship. Let's ignore the y relationship or the y information by staring right down the y-axis, more or less. I can't quite get it perfect, but that looks pretty good. And notice the relationship now. We see x and z. X is positive to the right, z is positive up. The z-coordinate is always the cube of the x-coordinate, and we see the cubic graph, right? There's a more complicated relationship between y and z because they have, let's see, z is y to the 3/2 power. Is how they're related. Can't quite get, there we go, something like that. So we get this kind of odd shape, right? So in each of these different directions, we kind of get a different sense of it, but overall, we've got this kind of a, right? There's not a name that I know of for this shape. It's just an odd path through space, right? In some directions, it takes on some very familiar forms, but in most directions, it's not something we're very, very familiar with. So let's turn our vector back on and notice what happens. As I scroll through values of t, the vector points at points on that line. All right, let's do it again. All right, so for each value of t, that vector is pointing to a point on the line, right? My software stops graphing the line when it goes above some value there, but we get the idea. Okay, let's take a look at another one. So let's look at our p of t, which is cosine of t. The x function is cosine of t. Then we have sine of t for the y function, and then simply t for the z coordinate. So one thing we might think about in visualizing this is the fact that we have this relationship from trigonometry. Cosine squared plus sine squared is always equal to 1. Well, in this case, that means my x coordinate squared and my y coordinate squared their sum is 1, okay? Which is another way of saying that the graph of this, in order to satisfy this, because it's x and y coordinates, their squares have to sum to 1, it must live on this cylinder, which is the cylinder with the equation x squared plus y squared equals 1, right? This is a nice cylinder that's traveling up and down the z-axis. This is not my space curve, but I know my space curve lives on here because any point of this space curve, so I should write this out explicitly, the space curve is the parametric equations cosine of t, sine of t, t. So when we'll say things like the associated space curve to the vector function, this is what we mean. We've got a set of, or maybe we write it as x equals cosine of t, y equals sine of t, z equals t, that we're taking the component functions of our vector equation and using them as parametric equations. That's the associated curve. So remember, let's open up our vector function now. Where did you go? Here we go. This is the vector one we already looked at. So that green arrow inside, notice it's hard to see exactly, but it is pointing at points along that cylinder where we said the curve has to live. Let's now add in this space curve. And we see that it does indeed live right on that cylinder, right? If we look down the cylinder, the space curve is simply a circle. And if I change values of my vector function, it just keeps pointing at points along that circle, right? And we can't see that the points are actually not repeated, right? There's some difference happening in the z coordinates that we can't quite see. Now let's see what happens. As our input increases, let's say we're going from a negative t value, so now I'm at negative 10 pi. As I increase, right, I'm traveling around that circle, just like when we made the parametric equations, cosine of t, sine of t in 2 dimensions, we traveled around a circle, except now my z coordinate is just getting larger the whole time. So I get this nice spiral moving up, and there's my vector equation pointing at all those points on the line. Let's get rid of the cylinder. We get this nice corkscrew shape. And again, if I scroll through my vector function, it spits out points along that line. Okay. Okay, so that is all I want to say about our introduction to space curves and vector functions, right? They're related, but I want to make sure we keep clear. We think of them differently. This vector, we sometimes think of the vector as the position vector when we associate it to a space curve, right? So in this case, P of t is the position vector, or the position function, depending on how you want to say it, or we could say position vector function for the space curve. I'll just call it S for now. Right? In other words, it points to points on that line. And then we think of that curve in a couple different ways. Sometimes we can think of it as a path through space. We also, we saw this a lot when we did some work on parametric equations in 2 dimensions. We can think of it as a point moving through space. And so we can imagine a little particle that's traveling through space this way, right? So in fact, let's see if I can quickly put a little particle on here. Yeah, there we go. So now we've got a particle that's traveling along that. So if you have something, right, some kind of, I don't know, an electron moving through a magnetic field might take some kind of curly path. That could be tracking its position. The space curve itself is a drawing of its path, and the vector function points to where it is at each moment in time relative to whatever origin you define. Okay, that's really it for this one. We'll do some more stuff with these space curves, how to build some more interesting ones, and then we'll get into some calculus on space curves in a couple videos. Thanks, everybody. See you next time.